All right, guys, welcome back. We're going to be talking about the common ion effect now. So we're going to be moving into that new topic. I'm going to go ahead and share my screen with you so we can talk about the same things. And I'm going to go ahead and move to the next slide so that we can look at what we're going to be talking about today. So moving to that next slide. Hello. Why are you not doing what I want you to be doing? Okay, give me a sec. Oh, there it is. Awesome. It took a minute. So we're going to be talking about the common ion effect. We'll talk about what that has to do with solubility. We'll talk about pH and solubility, okay, and see what effect we have from pH. We'll talk about complex ion equilibria, how we can form a complex ion and that can change the solubility of these insoluble salts that we've been talking about. And then we'll talk about the application of the solubility product principle to qualitative analysis. The last couple of things we're going to talk about are experiments 6 and 7. So experiment 6 is a paper-only lab. Experiment 7, there are some simulators that you guys are going to use to do that. There is some data available for you as well. So we'll talk about both of those. I will talk about them in brief here, and then there'll be a detailed lecture for each one of those so you know what to do. Okay? But both of those are next week, so we're not going to be worried about that. Oh, one other thing that I should mention. For my in-person class, I've moved back the due dates, for experiments 2 and, is it 2 and 3? No, 3 and 4. 3 and 4. So that rather than being like right after the test, they're going to be Wednesday of next week. I will probably be making the same change for you guys. I just want to make sure that I note that and actually write that down. Change due date for labs on D2L. Okay, so hopefully that will remind me that I actually need to do that. I may have done it today, but I can't remember, so I will be changing that. Okay, awesome. So that's what we're going to be talking about today. So let's get into it. Let's talk about solubility. Okay, so if we want to talk about the solubility of CaF2, right? So we want CaF2 to go into solution and give us a Ca2 plus and 2F minus. It changes. Our ability to do that changes as we have F minus already in solution. So remember, the equation that we're talking about when we talk about doing this is we're talking about CaF2 salt coming apart to give me Ca2 plus, which is aqueous, plus 2F minus, which is aqueous, right? And we've also, up until this point, we've always assumed that there was none of this stuff present. And so then when we do this, how much is soluble is going to be based entirely on the stoichiometry from the CaF2. So 1 Ca, 2 Fs every time this comes in. And there's nothing else that will affect it. But what happens if we actually already have one of these things here? Well, that changes things, right? From Le Chatelier's principle, we know that if we already have this here, and so that concentration is higher than we would expect it to be, that means that this reaction has to shift back towards the solid, which means that less of it is going to dissolve, so more of it is in solution as a solid and not as Ca2 plus and 2F minus. And that's because of the presence of the F minus already in solution. Okay, so that's an interesting thing, one that we really haven't dealt with so far. We'll get into the math that goes along with this. But we know that when there's a common ion, that changes our solubility. And having a common ion present means that we are generally less soluble than we were before. Okay? Now, how does that work? What does that look like? Oh, come on. Catch up. My computer's being very slow. Hopefully it will catch up. Because if it doesn't, we're going to... Okay, sorry. All right, so let's talk about this. So now I want to talk about what effect does that have, because we talked about it from a qualitative sense. So if F minus is already present, it's not going to be able to dissolve as much as we thought it would. And let's talk about what this would look like if we were talking about it by itself. So CaF2 on its own has a KSP of 3.9 times 10 to the minus 11th at 25 degrees. If we calculate the solubility of Ca2 plus, the KSP is equal to Ca2 plus times F minus squared. Okay. We know that our change, every CaF2 I put in gives me a Ca2 plus and 2F minus, right? So if we do that, and we take our x, 2x squared, that gives me 4x cubed. When I simplify that, I set that equal to 3.9 times 10 to the negative 11th, which is the KSP that I was given. I then do the division, 3.9 times 10 to the negative 11th divided by 4, and that's going to give me 9.75 times 10 to the minus 12th is equal to x cubed. I take the cube root of both sides, and so math cube root second answer, and that gives me x is equal to 2.14 times 10 to the minus 4th, which strangely enough is the number that's right here for the Ca2 plus. Okay, now I know that that's my molar solubility, and then if I want to know the concentration of the F minus, I have to multiply it by 2. That's how I get that 4.2 times 10 to the minus 4.27 times 10 to the minus 4. Okay, so that's my concentration of both of those species when it's just water. Okay, and they're both related to that X. But now we need to talk about what happens if we add 0.05 molar NaF to the water before adding the 0.2 molar CaF2. In that case, what's the solubility of Ca2 plus? Well, I still have that same expression, that my KSP equals Ca2 plus times F minus squared. But now, instead of having a 0 in both of these positions, my Ca2 plus is still 0, but my F minus is 0.05. Okay, that means that we still have the plus x and the plus 2x there. So technically, this would be the 0.5 plus 2x, but we know that we're going to ignore the 2x comparative to the 0.5, and therefore we're going to plug in to that 3.9 times 10 to the negative 11. That's equal to the x times the 0.05. And that 0.05 has to be squared because that's an F minus concentration. So we have to square that. Okay. Now that F minus concentration is fixed, and it's fixed by where I got it from, that NaF. So it's not related to the X that we're talking about for the other thing because they aren't related in any way, shape, or form. Okay. But to solve for this, I have to take that 3.9 times 10 to the minus 11th. 3.9 second EE negative 11, divide that by 0.05 x squared. And that gives me x is equal to 1.56 times 10 to the minus 8th, which is the number that's in that table. And if you look, we're talking about a difference between 2.14 times 10 to the minus 4th and 1.56 times 10 to the minus 8th. That concentration is hugely different. Okay? And that's what having a common ion does for us. It changes that solubility, and it makes it much smaller because of the excess presence of the F minuses there. Okay, so that's what we're seeing when we do that. Okay, this is how this new information is going to be added to our ice tables, because now we have a concentration of F minus that comes from something else. And remember, when we talk about that NaF is an ionic compound. It completely dissociates to give me Na plus F minus. So whatever this concentration was, that is that concentration and that concentration as soon as it gets into water. Okay, so I know that's true for anything that is an ionic compound that completely dissociates. Okay, and that's most of my ionic compounds. Not all of my acids, not all of my bases, because there are some other things going on there. But that's what we're talking about for that. Okay? So hopefully that's about as clear as mud. So let's see what we can do to make that stick a little bit better. So let's talk about the solubility of aluminum hydroxide on its own, and then the solubility of aluminum in the presence of 0.5 molar NaOH. Okay, aluminum hydroxide. So the first thing is I know it's aluminum, and I know I'm talking about hydroxide. Hydroxide is OH minus. And if I look at my aluminum, sorry, I need to find something. Go. How many times can I pull up a periodic table? Awesome. So if I yank this over here so we can take a look at it, I'm looking for aluminum. Aluminum is right here. And so that means that in this third row, he has 1, 2, 3 electrons that are present. We've yanked all of those off to go back and be like neon. So he ends up being Al3 plus. Okay, so that's the charge that he has. So he's a 3 plus, which means that I'm going to need 3 of those OHs. And so my AlOH3 solid is going to come apart to give me an Al3 plus 3 OH minus. And of course, because I know I'm going to need to do something with my I, my C, and my E, I'm going to set that up as my R in my raised. Okay, awesome. I'm going to talk about the solubility of the aluminum hydroxide on its own. I don't care about that solid because it's not part of what we need to calculate. Aluminum hydroxide is one of these salts that I need to be able to look at the solubility for. So I don't have a KSP. And so I'm going to look in my handouts that I was given, and on page 8, I see that aluminum hydroxide, AlOH3, has a KSP equal to 1.8 times 10 to the negative 33rd. Now this is something that you will see on the test. I don't necessarily put all of the KSPs with them because you have them available to you. So I don't necessarily put them on the test. Okay? So if you don't see it, make sure you look for it. Now, in the event that you still can't find it, then that's a different conversation we need to have. And you need to say to me, look, woman, you didn't give me all the information I need to be able to do anything with this, but here's what I can do. And show me what you know. And whatever you show me, I have to be willing to give you points for. Because if I didn't give you enough information to be able to solve that question, then I need to gauge what you do know based on what you wrote down. So giving me something is helpful. Okay. Now, we start with none of that and none of that. Okay. No, I know from a technical standpoint that's not true. I know in pure water, OH minus is equal to 1 times 10 to the minus 7th, but that's a really tiny concentration. So I don't care about it. Okay, so even if it's there, I'm not concerned about it. Every time an aluminum hydroxide comes apart, I get 1 aluminum and I get 3 hydroxides that come off of that. So I have an X and a 3X. Okay. That means at equilibrium, this is going to be X, this is going to be 3X. I'm going to have my KSP equal to the concentration of Al3 plus times the concentration of OH minus cubed. Then I'm going to have Al3 plus is X. My OH minus is 3X. That whole thing is cubed. And that's equal to the 1.8 times 10 to the negative 33rd. Okay. So if I do this simplification, I have 1.8 times 10 to the negative 33rd is equal to X times 3 times 3 is 9. 9 times 3 is 27. So 27x cubed times 1 more x is x to the 4th. Okay. So that's my simplification there. So I take my 1.8 second e negative 33. I divide that by 27. And that gives me x to the 4th is equal to 6.67 times 10 to the negative 35th. I then need to take the fourth root of that. So I take my second answer, I hit the little hat guy, the caret, zero parentheses, 1 divided by 4, and that gives me x is equal to 2.86 times 10 to the minus 9th. Okay? I'm trying to be consistent with sig figs, so this should actually be 2.9 because it's 2 sig figs because my KSP was 2 sig figs, so that's how I got that number of significant digits. So 2.9 times 10 to the minus 9th. Okay, this is a molar solubility, so this is moles per liter. That is also equal to the concentration of Al3 plus, and of course my OH minus on its own. 3 times that answer is 8.5, 8.6. And 10 to the minus 9. Okay, so those are my equilibrium concentrations when I am just dealing with pure water. The next case that we're going to deal with is going to be extremely similar, but instead of it being a situation where we have ALOH3 OH3 solid, associated to become Al3 plus 3 OH minus. That's still true. What's not still true is the values in my ice, specifically in my initial. So my Al is still 0, but my question up here says solubility of aluminum in the presence of 0.5 molar NaOH. So NaOH is a strong base. It completely dissociates to give me Na plus OH minus. If this starts as 0.5, that means I get 0.5 molar Na plus and 0.5 molar OH minus. Again, because it's a strong base. So this becomes 0.5 there. We then change up our what we're looking at. Our KSP is still concentration of Al3 plus times the concentration of the OH minus cubed. Our Al3 plus is going to be plus x. This is a plus 3x. 0.5 plus 3x. The 3x is small, so we ignore it. And that means that we're left with x for the Al3 plus times the 0.5 cubed. And that's equal to the KSP. So 1.8 times 10 to the negative 33rd is equal to 0.5 cubed, which is 0.125 x. So we take and we divide 1.8 times 10 to the negative 33rd divided by that answer that I just calculated, which gives me x is equal to 1.44 times 10 to the negative 32. And so this x is 1.44 times 10 to the negative 32. And again, big change. So way less soluble now than it was before. And that's because of the presence of that OH minus. So that's the common ion effect. So a couple of things that we need to pull from that is that one, our math changes. And that affects our initial condition, because as soon as we add that thing to it, it completely dissociates. And so we know what that concentration of this other thing is. And that when we're talking about common ion, that's how it always works. The other thing that we need to be able to talk about is the fact that since this OH is already here, so this OH right here is already present, that 0.5 there means that this concentration is high compared to what we would expect, which means that it shifts back this direction. So the Al3 plus does not stay as Al3 plus, it goes back to become AlOH3, which makes total sense, because if I have more OH minus, then it's going to react with the Al3 plus to make more of that salt. Okay, that's just how that works. So questions, comments, problems about that? Okay, let's see where we're next. Calculating solubility of the common ion. So what's the molar solubility of CaF2 in 0.010 molar CaNO32? So we start the exact same way that we always have. We have our balanced equation. CaF2 gives me Ca2 plus 2F minus. And KSP is then Ca2 plus times F minus squared, and that's equal to 3.9 times 10 to the minus 11th. Okay, I looked that value up in my table, and I found that CaF2 has that KSP value. Okay, awesome. So here's my R, that reaction that I have, the CaF2 going to Ca2 plus 2F minus. Initially, I have none of the CaF2. I don't worry about this at all. I have 0.01 molar Ca2 plus from the CaNO32. And I have none of that F minus. So the F minus doesn't change with the Ca2 plus. This one right here does. We then get our Ca2 plus is going to be a plus X. And of course, our F minus is a plus 2X, which gives us the following expression. So 3.9 times 10 to the minus 11th is equal to 0.010 times 2x squared. Now, you'll see that that's what this says right here. It's 3.9 times 10 to the negative 11th equals 0.010 plus x times the 2x. And we assume that x is way, way less than 0.010, so that 0.010 plus x just becomes 0.010, which is exactly what I wrote down. We now have the same expression down here as I have written out here. So 3.9 times 10 to the minus 11th equals 0.010 times 2x squared. And that gives me x equal to 3.1 times 10 to the minus 5th. Okay. If that is true, and that's my x value, then my Ca2 plus is 1 times 10 to the minus 2. And that actually should not be that x value. This should be 2 times that value right there. So 2 times that 3.1 times 10 minus 5th gives me 6.2 times 10 to the 5th. I forgot to multiply by 2. Go me forget my stoichiometry. That's awfully helpful. Okay, so that's what we're talking about there. So hopefully there are no questions, comments, problems about any of that. If there are, please let me know. Sorry, 2 seconds. Trying to do 2 things at once. I know, not a good idea. But in my effort to get things to you guys in a timely manner, I am trying to upload to YouTube while I'm recording my next lecture. It does take a hot minute to be able to get things to upload. And of course, I have to list it a little differently than most people do so that it can be readily available. All right, so that's another example of calculating solubility with a common ion. Okay, awesome. When we talk about if we're going to change, come on, you can catch up. You can do it. It can happen. Okay. Come on. Okay, so if we want to talk about the solubility of copper 1 iodide in the presence of 0.25 molar HI, we're not starting with our water case. Okay, that's not what we're doing right here. What we are doing is looking at our copper 1 iodide. So copper 1 is Cu plus, iodide is I minus. So we have a CuI solid decomposing to give me a Cu plus an I minus. Of course, that's my R. My I is going to be 0 for the Cu, and I is going to be 0.25. And again, HI is a strong acid, 0.25 molar is what they told me. So when that comes apart, I get H plus and I minus, both of which are 0.25. Okay, so both of those are that concentration, and that's where I get that initial concentration of I minus that I plug into my ice stick. My change is always going to be based on the stoichiometry. So for every copper iodide that breaks down, I get 1 copper and 1 iodide. So I end up with X in both of those locations. Okay? At equilibrium, we're going to have the copper being X and my iodide being 0.25 plus the X being really small, we ignore that and just leave it as the 0.25. That means my KSP is equal to the Cu plus times the I minus. And if I look at my solubility product constants on page 8, I see copper 1 iodide, CuI, is 5.1 times 10 to the minus 12. 5.1 times 10 to the minus 12 is equal to X times 0.25. And so X is going to be equal to 5.1 second EE to the negative 12 divided by 0.25. And that gives me 2.04 times 10 to the minus 11th. And actually, that should just be 2.0. And of course, that 0.0 is important. That is a significant digit. I need 2 sig figs, so I need both of those there. Sorry, it was bugging me. Okay, so that's my solubility of copper 1 iodide. So remember that this is in moles per liter. If I wanted to figure out what it is in grams per liter, I would need to multiply this by the molecular weight of that CuI. Now, didn't ask me for that, so I'm not going to do it, but that's how that would happen. Okay? So questions, comments, problems with any of what we've done so far? And I hope the answer to that is no. But if there is, then we should talk about it. Okay? Let's do one more example. Let's talk about the solubility of zinc in the presence of 0.36 molar NaOH. Okay, fine. Well, I'm looking at this going, all right, I think that zinc hydroxide is going to be insoluble. Let me check my solubility product constants. And I see that zinc hydroxide, ZnOH2, has a KSP value of 1.8 times 10 to the minus 14. So KSP equals 1.8 times 10 to the minus 14th, and it says ZnOH2, meaning my Zn is 2 plus charge. Yay. So there we go. That's my solid. We're going to take that apart to be a Zn2 plus, which is aqueous, plus 2OH minus aqueous. Don't care about any of the solid parts. My Zn2 plus is 0 to start with. My OH minus is going to be 0.36. And NaOH, strong base, completely dissociates, so that's where I get that OH minus concentration. I know that my KSP is equal to Zn2 plus, concentration thereof, times the concentration of the OH minus squared. And so I know that when the ZnOH2 comes apart, I get 1x for the Z and 2x for the OH. I also know that 0 plus the plus x is going to give me x at equilibrium. And the 0.36 plus 2x, ignoring the 2x, gives me 0.36. Right. So I take and I plug my x in for Zn2 plus, and I put my 0.36 in for the OH minus, and I have to square that because that's what the stoichiometry requires. And that's equal to that 1.8 times 10 to the negative 14th. So I take that 1.8 times 10 to the minus 14th, 1.8 second EE negative 14, and I divide that by 0.36 squared, and that gives me x equal to 1.4 times 10 to the minus 13. Sweet. Oh my God. That was so exciting. Let's not forget. Okay. Not only does the presence of a common ion affect the solubility of the salt, but it can also change the properties of the solution. So if a solution is a weak acid and we add the common ion, then you form a buffer. And that buffer will then have resistance to changes in pH, right? So that's something that we have to be able to look for and think about. The solution itself will be less acidic than it was because the acid is less soluble. And the solution is able to buffer the addition of acid or base due to the presence of the common anion. Okay? So having the weak acid and its conjugate base means that I have the ability to react with an acid if I add it. So the acid being added will react with the conjugate base to neutralize that. A base being added will react with the weak acid, and so that will be mitigated by that. And of course, what this means is, isn't it fun that we have to think about more than one thing happening in this beaker? Okay. Now, I'm going to try to give you some idea when we need to pay attention to that and when we don't. Okay. But it is something that we always need to be thinking about. Excuse me, I'm sorry. Because that can happen anywhere. We need to pay attention to what is in our beaker to see, is there anything else that might be able to react with? One of the things that we run into in the laboratory when we do the experiments for the solubility is that we find that we get an effect depending on how much we breathe on the solution. And that's because as I exhale CO2 into my beaker, that CO2 reacts with the water, and that then forms a buffer, which then changes the pH properties of that solution. So that's something that we have to think about. How we do these experiments can be extremely important. You know, if we want to control all of our things around it, then we need to be careful about how we do it. Water vapor can change things, oxygen, hydrogen, nitrogen, whatever those concentrations are, that can change things. So we need to be cautious, okay, and try and control as much as we possibly can. So, questions, comments, problems on what we've talked about so far? I hope not. But if there are any, please let me know. Let's see where we're going next. At least if it'll let me. So whenever I have a weak electrolyte, something that's only slightly soluble is a weak electrolyte. It does not, by definition, completely dissolve. And a strong electrolyte, so something like NaF that completely dissociates. If they contain a common ion together in solution, the weak electrolyte ionizes less than it would if it were alone in solution. Okay? This is true for anything, but particularly true in terms of acid-base equilibrium. Okay? Awesome. Well, that was fun. Now, I'm going to pause here because this is actually taking us into our next topic. So I'm going to stop sharing. I'm going to pause here, and I'm going to probably post these two parts, and then when I have additional portions of this lecture, I will let you guys know that. But this way you can get started on watching this. All right, I'll talk to you soon. Bye, guys.